Hi everyone. In this video, we are discussing problem number 797, all paths from source to target. It's a medium level lead code problem. Let's read the problem statement. It's a graph-based problem, as you can clearly see. So the problem statement goes like this. Given a directed acyclic graph, in short, let's call it DAG. Okay, given a directed acyclic graph of n nodes labeled from 0 to n minus 1. So there is no confusion about what those labels are. Okay, it's simply from 0 to n minus 1. So if there are, say, 10 nodes, the labels of those 10 nodes are 0, 1, 2, 3, all the way up to 9. So as you can clearly see, it's 0 indexed. Okay, now we need to find all possible paths from the node 0 to node n minus 1. Right, this is the objective. We need to find all possible paths from node 0 to node n minus 1. So when the problem statement says we need to find all paths from source to target, it's understood that, here they are making it very clear, it's understood that node 0 is counted as source in any given graph, and the last node, which is the node n minus 1, is the target, right? Now we need to find all possible paths, and we can return those paths in any order, right? So the graph is given as follows. So how do they represent graph? We know that there are few different ways of representing graphs. So here, how exactly they are representing the graph? The graph is basically a list of lists, right? Graph I is a list of all nodes you can visit from the node which is labeled as I. So there is a directed edge from node I to the node graph of ij. It may not be very clear if I simply read it out like this. There are some examples given. Okay, we'll head over to whiteboard. There we can understand these examples in a much better way. Okay, so they have given two examples. So here we have one directed acyclic graph, and like I told you, they are representing the graph using list of lists, right? And the output is supposed to be like this, and they have given some explanation. Okay, so let's go to whiteboard and try to understand this. Okay, so there is another example given. So this example is what we are going to discuss in whiteboard, right? So the graph is given as list of lists. Even our output is going to be list of lists, which contains all the paths from the source to the target. And n represents the length of the graph, which is the total number of nodes, which is given in the problem statement. And n ranges from 2 to 15, inclusive of both 2 and 15, because it's a slack inequality, as you can clearly see. And graph of ij can be any number from 0 to n, 0 included, n not included. But graph of ij is not equal to I, in the sense there is no node which is directed to itself. I'll explain that, right? And all the elements in the graph I are unique, right? It means we can't have two or more edges directly connecting a pair of nodes. There exists only one edge maximum from a node to any other given node, maximum one edge. The input graph is guaranteed to be a DAG, directed acyclic graphs. So these are the constraints given. So now let's head over to whiteboard and discuss these examples given. So one of the examples that you see here, the blue one, is the example number 2 given in Leetcode itself. And the other two graphs, the red one and the green one, I made it up to help you understand why we are very, very particular about directed acyclic graphs. Why can't it be just a graph? Let's check. So let's consider the above DAG, a directed acyclic graph, this blue one, which is the same example given in Leetcode, example number 2. Okay, so directed acyclic graph. Okay, directed in the sense what? All the edges are directed. So you can clearly see the arrowhead. It's like a one-way street. It is a one-way street, right? You can only go in one specific direction. You cannot go backward, right? Okay, so the blue one is a DAG. Now we have to justify, like, why directed, why acyclic? Okay, so first let me talk about acyclic nature of this graph. What if we allow cycles in our graph? In this second graph, the red color graph, you can clearly see there is a cycle. You look at this original graph, the blue one, you cannot spot any cycle at all. Whereas in this red graph, the second graph, we can clearly spot a cycle. It's a directed graph, by the way, because all the edges, they have direction, right? So obviously it's a directed graph, but it's containing a cycle, right? Did you spot the cycle? This is a cycle 0, 1, 3. It forms a cycle. This is not the only cycle. You can also say 0, 1, 2, 3. Even that forms a cycle. 0, 1, 2, 3. Even that's a cycle. Okay, let's just focus on any one cycle. Let's focus on this triangular cycle 0, 1, 3. Now, what is wrong in having a cycle in the graph? Everything is wrong. You see, when we have a cycle in the graph, and particularly when we are dealing with problems like, we are trying to find the number of paths, it's possible that we can get ourselves entrapped in a cycle, which is like an infinite loop. We'll be going over the same edges again and again indefinitely. And even if you come up with a clever way of exiting that loop, there is another problem. We can still have infinitely many paths. Even if we exit that loop, we have infinitely many paths. Okay, I'll show you how it works. So what is the source here? This node is the source, right? And what is the target here, or the destination? This is the target, because it's very clearly given in the problem statement. The 0, the node labeled as 0, is the source, and the last number, which is 4, is the target. There are 5 nodes, but since it is 0 indexed, the last number is not 5, it is 4. So that is our target, right? So our aim is to go from 0 to 4. There are a few ways you can go from 0 to 4. You can directly go from 0 to 4. That is definitely a path. Now think about it. Okay, what if I take this route? 0, 1, 3, 4. Yeah, that is another path, right? Going from 0 to 4. That way we can surely go from 0 to 4. And also consider this. 0, 1, 3, 0, 1, 3, 4. Even that is a valid path. Okay, so even if we exit that infinite loop, it is still going to give us infinitely many different paths. Okay, the path 0, 1, 3, 4, 0, 1, 3, 4 is different from the path 0, 1, 3, 0, 1, 3, 4. These are two different paths altogether, right? So you can loop this particular cycle n number of times and exit it anytime you want, right? So 0, 1, 3, 0, 1, 3, 0, 1, 3, 0, 1, 3, 4. Even that is valid, right? So we can have infinitely many paths from 0 to 4 if we have cycles as a part of our graph, right? So to overcome this particular issue, we don't allow any cycles at all in our graph. So that explains why we insist that our graph is acyclic. Okay, so now how do we justify the directed property of the graph? The acyclic thing is very clear. It has to be acyclic. Otherwise, we will have infinitely many paths. Okay, so why it has to be directed? Okay, so check this third example. Look at this graph, right? And I made sure that this graph is having no cycle. As you can clearly see, you cannot spot any cycle in this particular graph. But I also ensured that it's undirected, right? So you can clearly see we just have edges. We don't have directed edges. We just have edges. We can go back and forth. And that precisely is the problem. We can go back and forth. Okay. So this is our source. 0 is our source. And 4 is the destination, right? So let's talk about paths taking us from 0 to 4. 0, 1, 3, 4 is our path. Fine. 0, 1, 0, 1, 3, 4 is also a path, right? 0, 1, 3, 1, 3, 4 is also a path. You see, when we don't have a directed graph, we can always, at any point, we can always go back and forth between any two pair of nodes, right? So that will result in infinitely many different paths from 0 to 4, right? So these are the issues with graphs containing cycles and the undirected graphs, right? So that is why we are very, very particular that our graph is both directed and also it is acyclic, right? So this prevents us from going back and forth or getting ourselves entrapped in an infinite loop, right? It basically guarantees that we have only finitely many paths, if at all there is any, we have only finitely many paths from the source to the destination, right? Okay then, so let me remove these two examples. Let's focus on the directed acyclic graph. It is now totally justified why we have to deal only with this, right? Now, like I told you in the problem statement, they're not going to give us the diagram. They're going to give us list of lists, right? And we will have to, from that, we will have to picturize the directed acyclic graph, DAG. right? Okay, how should we interpret it? How should we read this list of lists, right? It is basically adjacency list, okay? And how exactly should we read it? Look at this graph, which is list of lists. Which is the 0th element, the element in the 0th index? Okay, this is the element in the 0th index, right? So what does it mean? It means that the node which is labeled as 0 is going to have directed edges to the nodes 4, 3, and 1. That is what we mean by adjacency list, right? As you can clearly see in this graph. So this particular node, which is labeled as 0, from which you have 3 outward arrows. One is going to 4, the other one is going to 3, the other one is going to 1. Yeah, so that explains 4, 3, 1. Okay, now what is the element in the first index? It is this list. The list containing 3, 2, 4. Again, how should we interpret this? This is the element in the first index, right? So we will have to consider the node which is labeled as number 1, and its adjacency list is 3, 2, 4. So we can expect to have an outward arrow from the node labeled as 1 to the nodes 3, 2, and you can see 4, right? So these are the adjacent nodes to the node 1, okay? So likewise, the next element is the element in the second index, which is just this list with one node, that is 3. So as you can clearly see from this node 2, there is only one outward arrow, which is pointing at 3, right? And the next one is this. It is sitting at which index? 3. And the list there is 4, which means from the node 3, we have only one outward pointing arrow, which is pointing at the node 4, right? And the last element, which is this, is an empty list. That means from the node 4, from the node which is labeled as 4, you don't have any outward pointing arrow. There are no edges, outward edges from the node 4. Did you get this? So this is how we read the adjacency list, and whatever they have given us graph, which is list of lists, it's basically is nothing but this adjacency list. Now it's a classic problem, DFS problem. So now how to solve this problem? We need to find all possible paths from 0 to 4. Okay, so it's a classic example of DFS, depth first search algorithm, right? So this is what we're going to do. This is our strategy, right? So of course we will have to start here, 0. Okay, look at its adjacency list, right? Now I take the first element, which is 4, and that itself happens to be the destination. That's it, over. That is counted as a path. Okay, we are done. Okay, keep it aside. Now again, the same 0th node. Okay, what is the next element in its adjacency list, which is 3? Okay, so 3 is here, 3. Okay, what are the elements in the adjacency list of 3? There is only one element, which is 4, right? So it is 0 to 3, 3 to 4. Yeah, that is our destination. Okay, we are done. So that is another path. Okay, we'll keep it aside, right? We'll, include all these things in our output. Okay, now we're not fully done with 0. When can we say we are done with 0? When we are done exhausting all possible nodes in its adjacency list. Only then we are done with 0. So look at this. What is the next element in the adjacency list of 0? 1, right? We counted 0, 4, 0, 3. Now we have to talk about 0, 1. So 1 is here. Now look at the adjacency list of 1. What are the elements there? 3, 2, and 4. So focus on the first element, 3. Now what is the adjacency list of 3? 4. Yeah, so that is one path. Done. Okay, so now go back to 1. Okay, because 1 is having some more elements in its adjacency list, right? So from 1, we could have gone to 2. If you're going to 2, from there we can jump to 3. From 3, we can reach the destination. Okay, that is another possible path. Again, backtrack, right? Now, again, we are talking about 1. From 1, we can go to 4. And that itself is the destination. So that is also another valid path, right? And that's it. So we don't have any other path to consider because we have considered all the nodes in the adjacency list of 0. And we went to those nodes and we have exhausted all possible nodes in their respective adjacency list. So we have, considered all possible scenarios, all possible cases. So these are the only paths from 0 to 4. right? So we will have to code it out. And this, as I have told you before, it's basically a DFS problem, right? So how to code this out? Okay, first let's create a variable called output. It is going to be an empty list to begin with. This is where we are going to collect all our paths. Okay, and now we are going to create a function, a recursive function, DFS function, okay, which is going to take two parameters. One is the node and the other parameter is the path. So what's our plan? We will have to hop onto a node and look at its adjacency list, and we will have to hop onto every single node in the adjacency list of the given node, the node under consideration, right? So how to do it? For nodes in graph of node, okay, I'll explain what it means if you find it confusing, right? For nodes in graph of node, what is even the meaning of it? Okay, so I told you we are going to create a recursive function. It's DFS algorithm, so it's usually recursive in nature, and the parameters are node and path. We'll right now focus on the node. Okay, so you have certain node under consideration. Okay, for example's sake, just for example's sake, let it be the starting node itself, which is the 0th node. Okay, node labeled as 0, right? So what is the meaning of for nodes in graph of node? What is graph of 0? Just now I told you, right? What is graph of 0? Graph is list of lists. Okay, so what is graph of 0? That is going to be this list 431. Now what are these 431? These are the adjacent nodes of the node 0, right? So how do you interpret this? For nodes in graph of node means we are iterating through every single node in the adjacency list of the node under consideration, right? So you have certain node under consideration and we are trying to hop onto the nodes sitting in the adjacency list of that particular node under consideration, right? Did you get this? Okay, so that is what we mean by for nodes in graph of node. Okay, now what are we going to do? If we are iterating through the nodes sitting in the graph of node, what are we going to do with those new nodes? We are going to recursively call the same function. Okay, DFS of nodes, comma, path plus node. Whatever is our path till this particular node, to that particular path, we are adding one more node, which is the node under consideration. Okay, so we are going to recursively call the function, DFS function, on these new nodes, and we are updating our path by adding the node under consideration. Okay, and this is, as you can clearly see, is recursive in nature. And why did I leave this gap? Of course, for the base case, right? We will have to stop this recursive call somewhere, right? It's simple. We're going to stop the moment we reach the end, right? So if node equals end, okay, so what is the end here? End is nothing but the last node, right? N minus first node. What is n? The total number of nodes in the graph. Okay, so how do you symbolically write this? Let me make more room. End is nothing but length of graph, which is number n, and of course we have to do -1 because it is 0 indexed. Okay, if there are 10 nodes, we are not going like 1 to 10, we are going like 0 to 9, so we will have to subtract 1. Okay, so that is end. So this is the base case, right? Once we hit the end, there we stop. That's it. Okay, and before stopping, of course, we will have to include the path in our output list of lists, right? Output.append path plus, of course, we will have to include the current node under consideration, which is the end node, right? And there it ends, right? Else we will have to keep on recursively calling the function, right? That's it. Okay, and of course we will have to call this function first. DFS of 0 comma the path has to be empty list initially, right? And we return the output. That is where we are collecting all possible paths, right? So let's head over to the Leetcode and code it out and see how it works. Okay then, so let's start with this variable output, which is an empty list where we are going to collect all possible paths. And end node is length of graph -1, like I have explained just a while ago. And we are going to create a DFS function. DFS taking two parameters, one is node and the other parameter is the path, right? And first let's start with the base case. If the node is equal to end, right? Once we reach the end, then we don't have to do anything more. We don't have to recursively call the function anymore. We will just append the path to our output list. Okay, output.append of path plus, it is not just path, don't forget the very last node, which is the node under consideration, the end node. Else, if we did not hit the end yet, we will have to keep on calling this function recursively. Okay, so for nodes in graph of node, I've explained what it means. We are basically calling every single node in the adjacency list of the node under consideration in order to just hop onto the subsequent nodes, right? So DFS of nodes comma path plus node, and we will have to first call this function, and the input parameters are 0 because 0 is where we are starting, and the path is going to be empty list to begin with. Okay, and we will have to return the output. So let's test run this code. Great, it worked. And let's actually submit the code to see how it performs. That's pretty good. Our runtime rate is 95%, approx 96%, and the memory usage is 76%, which is pretty decent. They both are pretty decent, right? I hope you understood the solution. Thank you for watching.